Today we're gonna talk about the introduction for the guide for mechanistic empirical design of new and rehabilitated pavement structures. What are the objectives of this new guide? This design guide represents a major change in the way pavement design is currently performed, since it provides a framework for future continuous improvement to keep up with changes in trucking, materials, construction, design concepts, computers, and so on. We need a new guide. There's an economic justification for an improved design guide. As you can see on the image on the right, the number of billions of dollars the United States government has spent in highway construction and maintenance has increased a lot in the recent years. So there's a logical explanation for the government to look new ways in design that can lower the cost and make highways more effective. There's also a need for replace of the AASHTO guide due to certain deficiencies in the design method. For example, in the climatic effects, they only took into consideration one type of geographical location, as well as only one type of subgrade, which makes these values non-representative. There's also the truck characterization issue, in which by the time the previous guide was made, the number of trucks has increased tenfold by now. So these values are also not representative. There's also a design life deficiency, since roads are now designed to last longer instead of 20 years. Now they are required to last 30 or 40 years. So this makes also a deficiency in the design. What are the benefits of this guide compared to the previous one? This design provides the tools for evaluating the effect of variation in materials on pavement performance. Since the mechanistic procedures are able to better account for climate, aging, present-day materials, and present-day vehicle loadings, variation in performance in relation to design life should be reduced. This capability will then reduce life costs significantly over an entire highway network.
The design approach provided by the guide has three major stages. Stage 1 consists of the development of input values for the analysis. One key step to this process is foundation analysis, which for new pavements includes the stiffness determination and evaluation of volume change, frost heave, thaw weakening, drainage concerns, etc. And for rehabilitation projects, it includes the investigation of distress types and its causes. Also, during this first stage, pavement materials characterization and traffic input data are developed. Stage 2 of the design process is the structural or performance analysis. This analysis approach is an iterative one that begins with the selection of an initial trial design. The trial design requires initial estimates of layer thickness, geometric features, initial smoothness, etc. It is analyzed incrementally over time using the pavement response and distress models. If the trial design does not meet the performance criteria, modifications are made and analysis reruns until a satisfactory result is obtained. Finally, stage 3 of the process includes activities required to evaluate the structurally viable alternatives. These activities include an engineering analysis and life cycle cost analysis of the alternatives. In summary, the design process includes consideration of the parameters shown on the screen. There are different ways for obtaining the design inputs for a design project based on the criticality of the project and the available resources. In general, 3 levels of inputs are provided. Level 1 provides the highest level of accuracy, and it requires laboratory or field testing such as the dynamic modulus testing on hot-mix asphalt concrete, site-specific axle load spectra, etc. Level 2 inputs typically would be user-selected, possibly from an agency database, or they could be estimated through correlations. And level 3 inputs provide the lowest level of accuracy, and they typically include user-selected values or typical averages for the region. For a given design project, inputs may be obtained from a mix of levels, for example, concrete modulus of rupture from level 1, traffic load spectra from level 2, and subgrade resilient modulus from level 3.
Pavement Serviceability Index was presented by the serviceability history of the given pavement. The PSI is obtained from measurement of roughness and distresses, example cracking, patching, and rot depth for flexible pavement, at a given time during the service life of the pavement. The smoothness model form is based on an additive combination of initial smoothness, change in smoothness due to the increase in individual distress, change in smoothness due to site condition and maintenance activities. Traffic characterization. Level 1. The recommended approach for high-volume roads requires the gathering and analysis the site-specific traffic data, including vehicle count by class and by direction and lane. Level 2 is similar to Level 1, requiring site-specific volume and classification data. However, state or regional axle load expected distribution for each vehicle class may be used to estimate loading over the design analysis period. Level 3 will provide the fault load spectrum data for a specific functional class of highway. The designer applies these default values to available or estimated vehicle volume data. Pavement material characterization. The material parameters needed for the design process may be classified in one of three major groups. Number 1. Pavement response model material inputs. Number 2. Material related pavement distresses criteria. And number 3. Other materials properties. Structural modeling of the pavement. The structural response models are used to compute critical distresses, strains, and displacements in flexible and rigid pavement systems due to both traffic loads and climate factors, temperature and moisture.
Design of rehabilitation projects. The guide presents procedure for utilizing the results for the evaluation of the existing flexible, rigid, and composite pavements and the design of HMA and PCC rehabilitation for these pavements. The structural design of this rehabilitation is very similar to that of the empirical design of new or reconstructed pavement, with the major exception that the existing pavement condition is fully considered. A trail rehabilitation design must be first proposed and then is evaluated using the design guide software, which predicts the key distress types and smoothness. Design reliability. Practically everything associated with the design of new and rehabilitated pavements is variable in nature. Reliability has been incorporated in the guide in a consistent and uniform fashion for all pavement types, and it's defined as a probability that each of the key distress types and smoothness will be less than the selected critical level over the design period. Some of the variations with the previous version of ASHTO design guide are that this version considers each key predicted distress and ED directly in the definition. In the approach taken in the guide, several design features other than thickness are considered to improve the reliability estimate of the design. The designer begins the design process by configuring a trail design, then takes the prediction based on the mean values of the key distress types and smoothness over the design life of the pavement. The standard deviation of the distribution of the distress is determined as a function of the predicted cracking. Using the following relationship, it's possible to estimate the cracking at the desired reliability. It's important to mention that if a pavement designer wants a 90% reliability for cracking, then the predicted 90% curve must not exceed some pre-selected critical value of cracking. To select an appropriate level of reliability, the designer must consider that the levels for each distress type and for the ED need to be equal. There's an inherent connection between the levels selected for each distress type and ED and the level of design reliability. More important, the consequence if failure, the higher the design reliability. Use all distresses and ED to ensure that they'll meet the design reliability requirements.